Right, in this part of the lecture, we will now dive into the continuous time Fourier series analysis equations and synthesis equation. Basically, when we take an input signal, continuous time that is periodic x of t with period t naught, we'll perform analysis equation using this equation 2 here, and the synthesis equation to reconstruct it using equation 3 over here. So what does that mean? Let us now write the equation over and explain it in detail. First, x of t is periodic and continuous time. For example, this is a periodic signal, t in seconds. This is x of t. And we have an amplitude of a here, and we have a square with period t naught. And we want to analyze this. Basically, we want to send this signal x of t into a Fourier analysis machine. And we want to find what are the cosine wave at a particular frequency, its magnitude, and phase. And what Fourier tells us is this. If my x of t is periodic, its period is t naught, therefore its frequency, its fundamental frequency, angular, is 2 pi f naught is equals to 2 pi over t naught, and t naught is this guy. The word angular here is because I multiply it with respect to 2 pi. Now, Fourier tells us that if I have such a periodic signal with t naught, I only need frequencies, cosines at 0 omega naught, 1 omega naught, 2 omega naught, 3 omega naught, and so on, k omega naught, where k belongs to the integer values. I do not need any other frequencies. That means I do not need 1.1 omega naught, 1.23 omega naught. I only need the integer values, the integer values times omega naught frequencies. And therefore now what we have is this equation. We have Ck, where this Ck is a Fourier series coefficient at the k omega naught frequency of interest. And this Ck will tell me the magnitude and the phase of the complex exponential that is required to reconstruct the signal. I have previously told you that we use cosine wave to reconstruct the signal, and now I'm telling you that we are using complex exponential wave. In a later lecture, you will see that cosine waves can be represented as complex exponential, and complex exponentials are in fact a more basic signal than the cosine wave. Right, let us now write the analysis equation, how to find the component of complex exponential at the k omega naught frequency for x of t. And this is given by the following equation. 1 over t naught, which is 1 over the period, integrate over the interval of 1 period, the original signal x of t multiplied by e minus j k omega naught t dt. And this is the Fourier analysis continuous time equation. The synthesis equation is this. Given that I have found for all ck, so I must find for k equals to minus infinity to infinity for all integer values of k. X of t is taking the ck that is found for k equals to negative infinity to infinity ck e plus j k omega naught t. So, what is k omega naught t? In the following figure, let us have a cosine wave with this period. Over t naught second, it repeats one cycle. And here, we say that it has a fundamental angular frequency of 2 pi divided by t naught, or equivalently 2 pi times f naught, where f naught is equal to 1 over t naught, where t naught is the period. What about k equals to 0? When k equals to 0, then there is no cycle being repeated. Sorry, there is no cycle per second. Basically, it is a DC value with amplitude 1. What about 2 times the omega naught? It means that I'm simply asking you to generate a sine wave or a cosine wave with 2 cycles per t naught second. So here, the figure shows that now, for this same period of t naught, I have 2 cycles. For the 3 omega naught, I'm asking you to generate a sine wave or a cosine wave with 3 cycles per second, and so on and so forth. With that understanding of what is harmonics and the fundamental frequency, let us now reinterpret this equation. Here, I'm asking you to take x of t to multiply by e minus j k omega naught t, integrate over 1 period divided by 1 over t naught to get the coefficients of interest at ck. When k equals to 0, this term is e minus j to the power of 0, which is the DC term. E minus j0 is 1. When k equals to 1, this is a complex exponential rotating 1 cycle every t naught second. When k equals to 2, he is a complex exponential rotating 2 cycles every t naught second. What we are asking you to do is to take the original signal of interest, multiply it with higher and faster rotating complex exponential, multiplying them together, integrating them to find the area under the curve of these 2 functions multiplied together, divided by t naught, to give you a complex value that shows how xt is related to this function. It measures how much xt can be decomposed into this particular complex exponential. Right? So with that understanding, we have shown you how to calculate the continuous time Fourier series, the ck, as well as using ck's for the synthesis equation to generate x of t, the original signal of interest. Remember that CK is typically complex, and it will be broken down in, it can be broken down into the magnitude as well as the phase in this form. So, in many books, the continuous time Fourier series is taught to you in the complex exponential representation, which is this first row here. The first row is a repeat of the previous figure. What is the continuous time Fourier series coefficient CKs? In the second row, it is a repeat of the previous equation, which is a synthesis equation. Given CK, how to generate x of t. In this slide, it is a slide showing the different representation of the continuous time Fourier series synthesis equation. We have the third row and the fourth row. In the third row, this is the combined trigonometric form representation of x of t. It shows you that x of t can be formed instead of the complex exponential equation, be formed as this equation, C0 plus 2 times CK as cosine values, as cosine waveforms of k omega naught frequency plus a phase shift. And you'll be wondering, well, what is slash CK slash? And this is the magnitude of the CK, because CK is a complex number. And what is VK? VK is because CK is a complex number, it can be represented as magnitude and phase. VK is the phase at CK. And in fact, if you now see this form is the equation that I have previously used in my example, where I decompose a signal into sum of cosine wave at that particular frequency with a known magnitude and phase. And this represents x of t. So for students who do not like complex exponential synthesis, they can use this equation to perform synthesis. Finally, in other textbooks, they do not use both this form. Instead, they teach Fourier series in this form. They will break the original signal x of t as cosine without any phase shift and sine without any phase shift. For those who understand that these two forms are the same, in fact, you realize that to get the phase shift, there is a deep relationship between the A case and the B case. So these three equations, x of t, generated using the sum of complex exponential versus x of t using the sum of cosine with phase shift, or x of t using sum of cosine without phase shift and sine without phase shift, they are the same. The difference is in the magnitude and phase used, but there is a relationship between them, and this shows you the relationship between the C case to A case and B case, as well as the C case with respect to the magnitude and the phase. Now, to prove, we'll give you two figures to prove in these two appendixes, and I will only briefly touch in the general idea. In this figure, we go from the complex exponential form to the combined trigonometric form. Remember Euler's equation, Ej theta equals to cos theta plus j sine theta, and E minus j theta is cos theta minus j sine theta. When we add E plus j theta and to E minus j theta, we get 2 cos theta. We realize that cos theta can be broken down into E plus j term and E minus j term. And this is why in the figure below here, in the complex exponential term, we use k equals to minus infinity to positive infinity to have all the complex exponential for both positive and negative frequency, while in the combined trigo form for cosine, we only use k equals to 1 to positive infinity, because what we have done is to have used the Euler equation to combine the positive complex exponential and the negative complex exponential at the k omega naught frequency to generate the cosine. So this is the typical idea. With this understanding, you can follow the math to realize the relationship between the complex exponential representation and the combined trigonometric form expression. What about this form, the A cosine and the B cosine related to the complex exponential? Again, we can use the Euler equation and expand this to bring us to this form, showing us this relationship. In this appendix, this is our argument. Let us begin with the trigonometric form, which is x of t is equals to a naught, which is a DC term, plus the ak's multiplied by the cosine terms, plus bk multiplied by the sine term. The complex exponential term is the ck's over here. We will move from the Fourier trigonometric form to the complex exponential form. How do we do that? We will use the following identities. E plus j theta is equals to cos theta plus j sine theta. E minus j theta equals to cos theta minus j sine theta. So this is the Euler equation. What about the expression 1 over j? Well, 1 over j is equals to 1 over j multiplied by j divided by j, since this is 1. So we have j over j squared. J squared is nothing but root minus 1 times root minus 1. So we have j divided by minus 1, and therefore the whole expression becomes minus j. We realize that 1 over j is equals to minus j. We also combine the Euler equation to show us a representation of cosine and sine. So we realize that cosine theta is the sum of positive complex exponential at theta plus e minus j theta divided by 2. And here sine theta is the subtraction of these two expressions divided by 2j. All right. Let us now write a sub k cos k omega naught t. A sub k, we bring it out. We substitute k omega naught t. So now k omega naught t is the theta expression here. And then now we just write fully this expression. The same we do for bk, sine k omega naught t. bk, we bring it out. We substitute the expression of sine k omega naught t with this expression over here. We then substitute these two expressions into this expression, and we group the term of the positive frequency as well as the negative k omega naught frequency, and we realize that we have this form. We can reduce this form further such that we will now see that it is, and we will group these terms together and identify that CKs are this expression, C positive K is this expression, C negative K is this expression, and we arrive at the complex exponential form. So to repeat, the proof going from a trigonometric form to a complex exponential form is nothing but a substitution of the various identities, grouping the expression of the positive complex exponential frequency and the negative complex exponential frequency, and identifying the relationships of AKs and BKs to CK, and we have this expression. So in conclusion, we found that these three forms of the Fourier series synthesis, the complex exponential form, the combined trigo form, and the trigonometric form are the same